So today I'm going to start a new lecture series on wind turbines, and essentially most of you know that wind turbines are very important machines which generate power, and there is a lot of possibilities using these machines. These machines are very important for mitigating climate change and so on because they are able to produce energy without consuming any fossil fuels for that matter. So I'm going to start a series of lectures on this topic, and today is lecture 1. I'm Dr. Ganguly. Now, the wind turbine has two main parts. The number one part is the main rotor or the rotor, and the second part is the tower. And you will see many of the wind turbines out there. They essentially have this pretty simple form, and the form is a tall tower and then very large rotating blades. So we can see that the wind turbine is a device which lets you extract kinetic energy from the wind, and the air passes through the rotor disc. This air in turn slows down and the kinetic energy from the air or the wind is removed. And then what happens is that this kinetic energy is used to generate power. Now, wind turbine is of course a key machine for clean energy, and it can reduce many of the problems which are caused by burning of fossil fuels. For example, if you have a large number of coal-based thermal power plants, you can replace them with wind farms, and that's going to greatly help you reduce the carbon footprint of this energy generation process. Now, if we look at any wind turbine, we are going to see a very large rotor. We'll come later to why this rotor has to be so large. But we'll see that this rotor plays a very key part in the wind turbine performance in terms of generating power. Now, the tower, of course, is necessary to keep this rotor at a sufficiently high level, because what happens is that the wind speeds near the ground is typically pretty low, and as you go high, the wind speed increases. So essentially, you want this wind turbine or the main rotor to function at a location which is sufficiently high. So that's the role of the tower. So these are the two components which are important for a wind turbine, and in this course I'm going to focus mostly on the rotor. So what we need to do is we need to create a simple model which helps us predict the power generated by the wind turbine. And to do this, we have to make several approximations. So for example, we are going to assume that the affected air mass does not interact with the air outside the rotor disc region. So here you are going to see the rotor disc region. Let me switch on my laser pointer. So essentially you see that this is the rotor disc. So we are presuming that this location here is for the rotor disc. Then there is flow coming from the upstream region. So the air enters here, it goes through this rotor disc region and then goes further down. Now essentially what we will assume is that the air which is inside this boundary, which is known as the stream tube, does not interact with the air which is outside this boundary. So this lets us use the different laws of fluid mechanics within the constraints provided by this stream tube. So this boundary has a circular cross section. The circular cross section will of course depend on the radius of the rotor. So typically if the radius of the rotor is r, then the area of this rotor disc is going to be pi r square. And the important thing to remember is that there is a rotor disc here, there is air upstream, and there is air downstream. Now, no air is supposed to flow across this boundary which is created by the stream tube. So the mass flow rate of air is going to remain constant at different locations on the stream tube. That is an important assumption which is going to let us use the different equations for fluid flow in the wind turbine model. So now let's further develop this concept. We have the concept of the so-called actuator disk, and essentially what will happen is that the air will come in from upstream and then it's going to slow down and then it's going to pass through this rotor disk. Now what happens is that since this air is slowing down, the stream tube must expand so that it can accommodate the slow moving air. So this is a very important part of the process because the mass flow rate is remaining constant. So this rotor model is known as the actuator disk model. So what happens here is that the pressure changes because of the presence of this actuator disk, and so this is the reason why thrust is generated and power is also generated. And in the actuator disk model, we do not care about the individual blade. So essentially this entire rotor is supposed to be one disk, which is the cause for the pressure change. Now this lets us do simple modeling, but also keep in mind that we are not accounting here for the geometry of the blades, for the type of the blades, the number of blades and so on. The blade is only coming in through the rotor radius. So the only thing which matters as far as the blades are concerned here is the rotor radius. Now, what happens is that the air will pass through the actuator disc and the static pressure will drop below the atmospheric level. So far out in front of the rotor disc, the air is at the atmospheric pressure, and then here it's going to drop below the atmospheric pressure after it passes through the rotor disc. The downstream air is going to have reduced speed and pressure, and this region is known as the wake region. So the wake is essentially the region which is far downstream here compared to the rotor disc. Now the far downstream static pressure must again come back to the atmospheric pressure because you want to establish equilibrium, and so as you go further and further from the actuator disc, the air gets back to the atmospheric pressure, and of course air speed here will remain low if the wind turbine is functioning properly. Essentially the air is going to cause rotation of this rotor here, and therefore some of the energy is going to get extracted, and so once the energy is extracted from the air will essentially slow down here. So high airspeed will be there in front of the rotor disc and low airspeed will be there behind the rotor disc. Now we can quantify some of this thinking here in this figure. So you can see here that the actuator disc is essentially simply extracting energy from the wind. There is no specific turbine design here in terms of the dimensions the rotors have and so on. So we are not considering chord here, the airfoil section and so on. So what's happening here is that far upstream, the velocity is u infinity, the pressure is p infinity. So the infinity simply means that these are far upstream of the actuator disc. Now as the air comes pretty near the actuator disc, the velocity is going to slow down to ud because the air is seeing this actuator disc present here, and so it's going to slow down in anticipation of coming near this actuator disc. The pressure is also going to start rising up. Now once the actuator disc has been crossed, the pressure actually falls to this level here given by PD minus. So PD plus is the air pressure in front of the actuator disc and PD minus is the air pressure after the actuator disc, and ud is the velocity of air at the actuator disc. So the subscript d simply means disc here. So we are using subscript d to refer to the actuator disc values. Now far downstream, this is the wake. So we have uw is the velocity here. We have p infinity as the pressure in the far wake, and that is going to essentially complete our flow field picture here. So far upstream is infinity, far downstream is W, and at the actuator disc is D. These are the subscripts we are using here to denote the velocities and the pressures. Now we can immediately use one of the equations we have developed before, the continuity equation here. Now if you guys are not familiar with this continuity equation, you can go and refer to my course on basic aerodynamics, for which I have put a playlist, so that will familiarize you with the basic equations which are going to be required in this class. So now continuity equation for this flow simply means that the mass flow rate is going to remain constant throughout, because remember this is a closed system. We are not putting in any mass here from outside the stream tube. That is an assumption. So essentially far out you are going to have rho a infinity u infinity. This is going to be equal to rho AD UD at the rotor disc, and then that's going to be equal to rho AW UW far downstream of the rotor disc. Now we are assuming incompressible flow. That means rho is constant, and this is pretty much reasonable because as far as wind turbines are concerned, they operate a at a pretty low speed of wind, because wind speed is maybe something like 6-10 meters per second, or very low number. So if you remember, the speed of sound is 332 meters per second. So essentially you are way below the speed of sound here. So you have incompressible flow. So the density remains the same across all these positions. So essentially the continuity equation lets you relate the velocities and the cross sections at these three locations, that is far out in front of the rotor disc, at the rotor disc, and far downstream of the rotor disc. That's the first equation we are going to use later in this lecture series. So to summarize today's lecture, we see that wind turbine is a machine which extracts power from the wind. It is a renewable energy device, and it has gained enormous importance in the last 20 years or so. And actuator disk theory makes modeling simpler because it lets you consider the entire rotor disk to be one actuator disk and does not bother about the number of blades being there, about the cord, the airfoil section, and all the details about the blade. Now, there are common theories between wind turbine and helicopter rotor, airplane, and marine propellers. And these theories have come up because many of these devices essentially use a similar thing, which is they are using a rotor to generate power or to use power. So what happens with the helicopter rotor and the typical propellers is that those machines consume power, and the objective there is to generate thrust. Whereas the wind turbine actually generates power, and whatever thrust is produced is a byproduct. You cannot do one without the second, and therefore the wind turbine is a somewhat different type of device in that it generates power out of the wind. So to end this lecture today, we have essentially developed a basic formulation as far as the actuator disk is concerned, and we have figured out that there is a stream tube and the wind goes through the steam tube, it slows down, and the kinetic energy is extracted by the wind turbine, and this is going to be used to generate power. In the next lecture, I am going to also look at momentum theory based equations, and then in a following lecture we are going to look at the blade element momentum theory, where we are going to bring in some of the details about the rotor plates themselves. Now if any of you are not familiar with some of these equations, please go through my basic aerodynamics playlist, and that will familiarize you with this topic. So I will end this lecture here, and I will see you in my new video. Please put any comments you have about this lecture or any questions you have in the comment section below. See you then.